Welcome to the fourth lab of EC114. Today we'll look at some further use of the summary statistics capabilities of Stata. We will look at some scatter plots. We'll introduce OLS regression, predicted values, and how to graph predicted values with confidence intervals. And we'll just run one or two commands with multiple regression, so you have a basic understanding of how to do it in Stata. We will use the Stata regression command, regress command, to perform the OLS regression, but we'll also look into how to calculate the alpha and beta coefficients using the egen command. So first and foremost, let us set up our working directory and close any log files and start our log file for today. We will use a dataset that is going to be available in the description of this video with the remainder materials, and this dataset is called Eurostat and has some basic information on country, has a sample of countries, and has some basic information on labor productivity, R&D expenditure, education expenditure, and GDP growth. You have a description of these variables right here: labor productivity per hour worked, labor productivity per worker, R&D expenditure, public expenditure in education, GDP growth. So all the variables are numerical. Country is a variable that is labeled as a nominal variable, but we don't have to make any changes to these variables, and we can start using them right away. So first, let us derive some basic summary statistics for these variables. So we can either use a summarize command repeatedly like this, or we can simply list the variables after the summary command, and we generate one table of summary statistics for all of them without having to do it by hand in our code. Is a little bit neater. So here we have labor productivity per hour worked, the mean, and all the other summary statistics that we're going to be interested in. Here per worker, R&D expenditure, and public expenditure in education. Whenever you're starting to work with any data set, your main concern should also be to check for missing information, for missing data, because that can impact and debilitate the way in which you can use that data for whatever reasons. So if we type in codebook and we give all these variables, we have an idea of whether there are any missing information that we'll have to deal with, and it seems there are 8 missings for R&D expenditure and 3 missings for education expenditure, so we'll have to deal with this later on. So first, let us draw a scatter plot between labor productivity per hours worked and R&D expenditure to see whether there is some kind of relationship, and we can clearly see that there is a positive relationship between these two variables, which may be non-linear diminishing returns, as we can see that for higher levels of R&D expenditure, we're not getting higher levels of labor productivity per hours worked, but actually lower levels. So it kind of grows until an R&D expenditure of about 2, and then starts to decrease afterwards. So it may be that we do have this nonlinear relationship, or simply that these countries over here and over here are going to be outliers, and these outliers are very important because they will impact our analysis in peculiar ways, and we'll see that in a moment. So it may be interesting at some point to remove these outliers and see how our analysis will change. So first, let us obtain the OLS estimates for A and B in the model A plus B times X plus E, where Y dependent variable is labor productivity per hours worked and X is RD expenditure. So essentially we want to calculate B, our coefficient, and A, our alpha parameter, so our constant in the model, the intercept, and we're essentially going to use Stata to calculate this formula. So Stata does this automatically with the regress command, but it's important for us to understand how these values are generated, and we can do that using Stata. So first, let us make our two variables equal in terms of the missing data. So we don't want to be using data that is going to be missing for the expenditure but not for labor productivity per hour, because that will affect the means in the overall variables we're going to create. So first, let us replace labor productivity per hour equals to missing if RD expenditure is equal with double equal signs to missing. This is somehow restrictive in our data, because by changing the variable itself equals to missing, we're losing information in this data set. So most often you will want to create a new variable and replace that variable equal to missing. So for the purpose of this analysis, we can do this, and we won't save the data set and replace it. So first, let us create X bar. X bar is simply the mean of X, as we have here. So we're going to calculate the mean of X, then we'll calculate Xi, and the sum of Xi, we'll do the same for Yi, then the sum of Xi Yi, and the sum of Xi squared, and then we'll calculate this division, and then we'll just calculate A in a straightforward manner. So first, let us calculate X bar. This is a new command, egen. You can look at the options of egen by typing up help egen. It is a nice command because it generates new variables as functions of other variables, and there are many different functions that are going to be useful for all kinds of data analysis, and you can look at them here. So one of them is the mean, so it creates a constant within a variable list containing the mean of the expression. The expression here is the variable that we feed into the command. So our X variable is RD expenditure, and the Y variable is labor productivity per hour. So let's first create X bar. Then we create Xi, which is simply going to be X minus Xi minus X bar. So this will subtract for each observation of RD expenditure. It will subtract the value for X bar, so we can tabulate X bar here, so you can understand what it looks like. So it only has one value, and of 1.41169, and this will be the value that will be subtracted from each observation, so from each value of RD expenditure. So we create Xi. Now we move on to creating Y bar, which is going to be the mean of our Y, labor productivity per hour, again with the egen. Then we generate Yi equals to labor productivity minus Y bar, so equivalent to what we did with X bar. Xi. Now we can create Xi squared. This is simply Xi, our new variable, Xi elevated to the power of 2, which is done with the hat sign. Then we create Xi Yi, and then we'll take the summation of this to have the numerator in our B coefficient equation. So to get the sum, the total sum of xi, yi, we can use the function total, and the function total will simply sum all the values of xi, yi along the column. So if you look here, so it will sum all of these values and we'll have the total next to it. So these are all the variables that we just created. So Q will be the sum of xi squared, and P will be the sum of xy, so xi, yi, and essentially our B coefficient is equal to P divided by Q. And we can display our B coefficient, so 22.19. We'll do the same with alpha, so alpha simply equals to y bar minus B times x bar. So we already calculated B here, so we can calculate our intercept and display its value, 49.87. We can also calculate the r squared. So the r squared is simply going to be like b squared times the sum of xi squared over the sum of yi squared, and we already have all of these values calculated, so we simply have to create yi squared, and this is a different way of creating the squared value for the variable, and we just have to create the sum of this variable, which is going to be using the total function, and we now can create the r squared variable and display the r squared for our regression equation, 0.408. So now we can compare all our values with the regression output and see whether we were successful or not. So the value for our constant was 49.87, so we can actually just display them very quickly. Display B, A, and r squared, and looking at our output, r squared is exactly what we calculated. Our coefficient for rdx is exactly what we calculated, and our coefficient for the intercept is exactly as we calculated. So calculations were correct, and now we have a better understanding of what state is doing under the hood. We can predict, generate predicted values for y and the residuals as well. So this is done using the predict command, and then you add the option xb for the fitted values and residuals to obtain the residuals, and then you give it a name. So here y hat 1, so this is the first regression we run, and you can name it essentially whatever you want. So but you have to do this after running the regression that you want. So in this case, regress labor productivity per hour and RD expenditure. So let us generate both, and we will have them here at the end. So our fitted values and the residuals, and we can confirm that. So if we exclude these, we can confirm that the residuals are essentially going to be the y values minus the predicted values. And that is exactly the values we get here. So we can graph this fitted model using a two-way plot. So essentially we feed two plots into this two-way plot. First one is a scatter of labor productivity per hour and RD expenditure. The second one is a linear fit. It's essentially going to plot the predicted values between labor productivity and RD expenditure. And as an option, we add a title to it. And as we run this command, so we can see clearly there's a positive relationship between the two variables. However, the slope of this line may be pulled by these observations over here, so we can actually add the option to label and that has to be added when we scatter. So there is a bit of an overlap here, but we can see that these countries over here are Sweden and Finland, and so they're repeated here because we have a panel data structure, so we have countries per year, and that is what is causing this slope here to come down. So these outliers. So if we remove these outliers, it's likely that our regression coefficient will change. So the exercise now is to run again the regression by removing the outliers and then rerunning the scatter plot to see the difference. So if we first to identify these outliers, let us first sort the variable. So this will rank order the variable and list labor productivity in the last observations, in the last 20 observations. So here we have missing data, and then we can see that the outliers are going to be these countries over here, so where labor productivity per hour is above 130, so above 130, so are these countries over here. So we can confirm that by listing also country name. So if we again look at our plot, so Luxembourg is over here, so these are the outliers on the y-axis here, Luxembourg, and if we do the same with RD expenditure, we're going to find Sweden and Finland. So RD expenditure above 2.58 are the outliers that we see on the graph. So we're going to have to remove these outliers from our regression and compare with the previous results. Here, however, we cannot simply replace the variables equals to missing values, because then we cannot compare it to the previous regression. So we're going to create a new variable called out for outlier. We're going to generate this variable equals to 0 for all the observations. So all the observations are now going to be equal to 0 for this variable, and we will place the variable equals to 1 if labor productivity is larger than 150, so what classifies as the outliers in our graph, and equals to 1 if RD expenditure is larger than 3, also what classifies it as an outlier in the graph. And we're also going to replace it equals to missing if RD expenditure is equal to missing. Okay, so now we can simply run our regression again and compare the results with the previous one, but here we're going to impose the if condition, out equals to 0, so we're only interested in the regression between labor productivity per hour and R&D expenditure if the country is not an outlier. So before we had all the countries included, now we're going to exclude these countries and these countries. And if these observations are affecting the regression slope, we should expect a steeper regression line along the way. So let us run the regression. So here's the coefficient for R&D expenditure, so it's going to be higher than our previous regression where the outliers were included. And we can also observe this graphically, so we can generate a scatter plot for the regression where the outliers have been excluded, but for a visual comparison with the previous model, we can essentially get the scatter plot for labor productivity and R&D expenditure, then get a linear fit for the model where outliers are not present in the model, and for the model where outliers are present in the equation. So essentially we get two lines. This line represents the regression where outliers are not included, and this line, the green line, represents the equation where outliers are included. And we can see the difference in the slope between these two lines, and that is due to these observations over here that are affecting the slope. Now we're interested in finding out whether the difference in the coefficients between Model 1 with the outliers included and Model 2 without the outliers included, whether this difference is statistically significant. The reason being that if there is a difference between the coefficients, and if that difference is statistically significant, we will have to choose between the two models. And if the outliers are having an undue impact on the coefficient estimate for R&D expenditure, we may want to use the regression without the outliers in it. So we will use the lincom command for a simple linear combination of the two coefficients, and for that we'll have to run the two regressions again and compare the coefficients. So a nice package instated to compare results from different models is the stout package, which you can install by typing in sse install stout, and when you run this, it installs the package, and then you can use combine this package with estimates command, which stores the estimates from all the models you run, and then you can compare them using stab. So if we regress labor productivity on R&D expenditure and we store these estimates as M1 or Model 1, does not really matter as long as you type in estimate store and you give it a name. So we have stored the estimates of Model 1. Now we run the model without the outliers, and we store the estimates as Model 2. And now we can neatly compare the two models by typing stab M1, M2. And you can compare other models as well. So if you have multiple models, you can compare them all here. So we can see that there is a large difference between these two coefficients, and the lincom command will allow us to test whether this difference is statistically significant. So let us regress the second model again, so that the linear com command can extract the coefficient for R&D expenditure and subtract from that the coefficient 22.2 from the previous model with the outliers included. And so it tells us that the difference between them is statistically significant, and we will just keep working on the model without the outliers. So from this model we can predict y hat, again the residuals, that the fitted values. We can predict e hat, the residuals, and we can predict the standard error of the forecast, which will allow us to generate confident intervals for the estimates, and with that plot not only the fitted line but also the upper and lower bound of the confidence interval. So let us run these commands and generate these variables, and we will use the inv detail command to retrieve the upper and lower bound, and this is essentially, it returns the upper tail student's t-distribution of the form inf tail n comma p, where n is going to be the number of observations, p is going to be our critical value, so here is 5%, so two-tailed, and t is going to be then multiplied by the standard error of our forecast to added to y hat to retrieve the upper bound, and we'll do the same for the lower bound. So let us generate both of these, and what we will have is essentially, for the fitted values, if we look only at the fitted values, we'll have fitted value for our dependent variable, the upper bound and the lower bound, and we'll have this for all the observations for which we calculated them, and we can essentially plot them. So two-way scatter, we'll do a scatter plot between the two variables, we'll generate a linear fit between them, and using the option line, we'll generate a line with the upper bound NRD expenditure, which will be the upper bound of our prediction, the lower bound, all if our, for the case where the outliers are excluded, and this is the plot, so the upper bound and lower bound confidence intervals with the fitted regression line. When adding other variables to our regression, the regress command simply takes it as another covariate here. So if we want to include education expenditure to predict labor productivity per hour, we simply add it to the regression line, and again, running it for the case of with no outliers, it simply is added on here in the regression output. So a few words on the regression output: gives you a column with the coefficients, standard errors, t-statistics, so essentially the coefficient divided by the standard error, the p-value, so how significant are our estimates, confidence intervals, gives you number of observations, r squared, residual sum of squareds, and other information over here. Essentially now you'll be more interested in looking at the magnitude of coefficients and direction of the effect, at the r squared for your model, how well does the model fit the data, and whether your variables are significant predictors of your dependent variable or not. Again, you can add some scatter plots of your dependent variable and the new independent variables you're going to include, and try to understand whether there are any relationship between them, and then later on include them in the regression line. Here we're simply trying to point out whether there are any outliers in the education variable, and by excluding these outliers we're trying to see whether the coefficient in our regression changes, but as you will see when you run this on your own, you will see that the coefficients are not statistically significant, so I leave that as your homework. And finally, let us close our log file so that we can look at it later on.